Welcome to the fourth chapter of the time series course. During the previous weeks, we looked at stationary time series. Now, as of today, we will dive into non-stationary time series. And we will start with a short introduction and then discuss our first non-stationary process, namely the trend stationary process. We will then continue with the main building blocks needed to deal with non-stationary asymptotics, such as our partial sum process, Brownian motions, and the functional central limit theorem. Finally, we will start looking at unit root tests, which are tests that can be used to determine whether our time series is stationary or not. Let us start with a very easy example. On this slide, I have included the GDP in the Netherlands. And as you can immediately see from the plot, this time series is clearly not stationary. It is gradually increasing over time, so it has a trend. So the expected value is clearly not constant over time. And that violates, of course, already the first property of weak stationarity. Now, this is, of course, only one example, but there are many time series that are non-stationary. So we also need to be able to have the appropriate tools to deal with these time series. Now, today we will mainly focus on two non-stationary processes. Let's say that we work for now with models where we have IID errors with mean 0 and variance sigma squared, so finite. The first model we will look into is a deterministic trend model whose model equation is given over here on the slides. So we regress yt on a constant alpha, a time trend, and we also have our IID error. In a trend stationary model, the deviations of our time series around the trend line are the errors. And so since these are IID, the deviations around the trend line are stationary. So the movements of our time series around the trend, the deviations, the oscillations around the trend, are stationary. And that is why the time series is called a trend stationary process. Another very different model is the so-called random walk model with drift, whose model equation is also given over here on the slide in several versions even of it. We regress yt on its previous value, a constant delta, and we also have our IID error. Alternatively, we can also write the model for the series indifferences. If we just simply bring yt minus 1 to the left-hand side, we have yt minus 1, which is nothing more than the series indifferences that is indeed equal to our constant term plus our error term. Yet another equivalent formulation of our random walk model is given over here, where yt is expressed in terms of all of the lagged error terms. Now, how do I arrive at this expression? Well, just simply start from the model equation over here and use the trick of recursive substitution. So plug in the model equation for yt minus 1, which is yt minus 2 plus delta plus the error at time point t minus 1, and so on. And then you will see that you have the trend term that is popping up delta times. And here is the partial sum of the error terms up until time point t appearing. So we see that the deviations around the trend line given by these over here are not stationary. since we have a dependence on t error terms popping up, so the sum runs until time point t, we have a dependence on t. In this model, yt is called difference stationary, because you indeed need to take the series in first differences, as shown over here, to arrive at a stationary process. Now, in both cases, the deterministic trend model or the random walk with drift, yt is clearly not stationary. And so you can verify in your tutorial that conditions or which conditions of weak stationarity are violated. Now, both are non-stationary, but there are important differences between them. For the first case, you can actually just remove the trend by detrending. So running a regression of yt on a constant and a time trend, and then you can just continue to work with the residuals of that model, which are stationary. For the second case, so the random walk with drift, this procedure will not work to create a stationary time series. Instead, you need to difference the series in order to get a stationary time series. And so as they behave very differently, and we typically transform the series in a different way to get our stationary time series, we would of course like to have a test that can tell us whether we have a trend stationary or a different stationary series. And this type of test is what we call a unit root test. Now, you might have seen unit root tests already during the bachelor, and then you can probably remember that the test had critical values that were special, different from the ones that you were used to. Now, during these lecture videos and also the ones from next week, we will derive the limiting distributions of these test statistics. And we will start with inference for trend stationary time series processes in the next video.